Hello, it's Scott Manley here. If you've been following space and spaceflight for the last few months, you've probably heard a lot about Comet 3I Atlas. The 3I tells you that it is the third interstellar comet. Although technically Oumuamua didn't show any cometary activity, but it still got a comet designation. Nevertheless, Atlas has been pretty special because it came through the solar system faster than anything else. It was discovered prior to perihelion. And that gave scientists lots of time to plan observations for this using every instrument they could find. Now, unfortunately, it was quickly realised that the comet would come to perihelion, that is the closest point to the Sun, on the other side of the Sun from the Earth. On the other hand, it was going to come fortuitously close to Mars and Jupiter. And so during that closest approach in October, a number of spacecraft around Mars used their instruments to analyse the comet. But because of the government shutdown, NASA was unable to release any of that information until yesterday. And I'm definitely going to talk about those, but I actually want to start by rewinding to some of the earliest observations which were made. And I actually want to start off with observations which were made before its discovery. How is that possible? Well, discovering the object means actually identifying it, but it turns out that lots of spacecraft are pointing cameras in all sorts of directions across the sky. One of them is the Transiting Exoplanet Survey Satellite, which is designed to look for exoplanets, and it does this by looking for small variations in the brightness of many stars. Well, that data was found to include Comet 3I Atlas. So the team took this data and they basically started stacking the frames. That is, they added the frames together so they could reduce the signal to noise ratio and get brightnesses for about a couple of months prior to the discovery. The idea was, could you see any rotation signatures in this? And as cool as all that is, we still don't actually have any good data on whether it's rotating or not, because comets produce a cloud and the cloud tends to hide any variations in the light curves. Days after discovery, some near-infrared telescopes, namely the Gemini South and NASA's Infrared Telescope Facility, were able to look at the cloud surrounding the nucleus, and they did find what they believed was evidence for water ice. And that's not a surprise, that's kind of what you'd expect. Now we move to the Hubble Space Telescope. So the early Hubble observations were primarily photometric. What they were doing was they were looking to see if there was a cloud of dust, a coma. They wanted to see if they could pick out evidence of the nucleus and get an idea of the size of the object. So they did actually find that there was evidence of a coma of dust coming off. Because they definitively observed a dust cloud around the object, it meant that they could put at best an upper limit on the size of the object of 2.8 kilometers. And their measurements suggested that the coma was being fed by maybe tens to hundreds of kilograms of material every second. Of course, Hubble is no longer the biggest telescope that NASA operates. The James Webb Space Telescope had a chance to point at the comet in early August. And in addition to offering a larger aperture, JWST is able to look deeper into the infrared and perform spectroscopy there. And infrared spectroscopy is interesting because that is where you find those signals from the connections between molecular bonds. Using this, they were able to identify some signature peaks of various molecules. Water, obviously, and carbon dioxide. And the mind-blowing thing they discovered was that this was sending out way more carbon dioxide than water.